This is a 6-axis robot, so of course it has 6 individual joints. But what's unique about it is that each joint is made with these individual stepper motor and belt-driven actuators that are wireless. Now before you say, hey, I see wires on the robot, so how is it wireless? Let me explain. What I mean by wireless is that there are no wires that connect the joints to the central controller. Each joint is independent and has a controller and power supply of its own. This is one of those projects where it would be fair to ask, but why? Unfortunately, I'm silly enough to ask why not. But this approach of using independent joints might have some merit, and in this video, I want to show you what went into building the 6-axis robot, what worked, what didn't work, and what are the pros and cons of this approach. In my previous video, I built a belt-driven wireless actuator that had massive torque and position feedback. It worked well, but it had some issues which needed to be improved. So since then, I have made a few changes to the mechanical design of the actuator. I'll walk you through those specific changes here, but for a more detailed explanation about the actuator itself and its testing, please check out the previous video in the description. In the old design, we had the same 2-stage belt-driven reduction, but inside I was using this idler in between the 2 active pulleys. My goal with the idler was to engage as many teeth of the belt and the smaller pulley as possible by making the belt wrap around the smaller pulley a bit more. What I realized with a bit of trial and error is that the idler is not necessary. The engagement of the belt and the small pulley without the idler is enough. So I have gotten rid of the idler to make the length of the actuator smaller. Another change is that in the older design, I was using a shaft coupler to connect an arm to the output shaft. The problem here was that the shaft coupler slipped when the actuator had to apply higher torque. So I got rid of the shaft coupler. Now I'm using a disc to directly connect to the output pulley. Any arm can be bolted to this disc. Additionally, I also designed this single stage and more compact actuator for use in the distal ends of the robot. That takes care of all the mechanical design improvements. That went surprisingly smoothly. I was almost starting to think that the engineering gods were really blessing me for this project. But I might have spoken too soon. On the electronics side, the road to achieving improvements and making changes was quite bumpy. This older PCB I was using had a very large footprint, so I had to split the big PCB into 2 separate PCBs. One PCB for the Adafruit Qt Py, which is a nice and compact ESP32 based board in a smaller form factor, and the second PCB for all the power related components like the stepper driver and the battery terminals. I designed the circuit and sent the files to a PCB manufacturer. To save money, I thought I could just get a single layer PCB made, but when I got the PCBs delivered, I realized that the single layer PCB doesn't have a silk screen on the other side, so I can't use through-hole components with these. In hindsight, that should have been obvious. I even got as far as soldering a few components on this PCB only to realize I can't use it. So then I had to order these 2-layer PCBs and of course pay for these too. I was really feeling silly and poor. I wanted some progress, so I soldered the PCBs. The terminals are too close to each other, but I should be able to live with that. Let's see if the motor moves first. I'm almost certain the code and the wiring is fine. Why won't the motor move?
A few moments later.
Why is the voltage on the VMOT negative? After some debugging, I realized that the battery terminals were wired wrong. That seems to have fried the stepper driver. Now I was feeling more silly and poor, so desperation was at its peak. I wanted to make this work. After some more soldering and rewiring, the motor is moving. Progress. Why is this so hot? I'm pretty sure I set the current limit. I was now feeling silly, poor and burnt. After a while, I figured out that the DRV8834 stepper driver I'm using is not rated for a current as high as my stepper motor is drawing. This wasn't an issue earlier because I was using a different stepper motor and I never ran the entire setup for such a substantially long time. But now I'm going to use this heat sink and fan to cool the stepper driver. I have monitored the temperature with this laser thermometer here and it has been fine so far. Regardless, I will keep monitoring the temperature of each one of these as I move forward. But for now, this seems to be working fine. Finally. Now, in order to coordinate the movements of all of the joints, plan is to use ESP-NOW wireless protocol. I'm using ESP-NOW because it is very fast and ideal for situations that need low power consumption. All you have to do is pair the sender and the receiver using their MAC addresses. The downside of this is that ESP-NOW cannot handle high volumes of data, but we should be more than fine with that because all we are sending and receiving are floating point angle values and acknowledgement signals. So a central controller sends joint angles to the Adafruit QT-Pi, which acknowledges that it has received the joint angles and makes the stepper motor move to its position. While doing so, it also reports back the joint angle being measured by the AS5600 magnetic encoder, achieving feedback control. For the future, I plan to put PID control in the joint itself to achieve a feedback loop, but that will have to wait for now. Let's see how all of this works. I can send a joint angle to a joint. In this trial, we only have one joint. The joint receives this command, acknowledges that it has received it, moves to the joint location and then reports back its final location to the central ESP32 controller. Right now, because we don't have closed loop control, we receive the joint angle feedback but don't do anything with it. So you can see there is a discrepancy in the angle we sent the motor to and the angle that was reported back. Once we have closed loop control with PID, this shouldn't be a problem. As you can see, the ESP-NOW protocol is actually very fast. The turnaround time, or TTT, which is the time required for the command to reach the controller and then for the controller to revert back with an acknowledgement, is almost imperceptible. Alright, now we can move on to the mechanical assembly. Now that the actuators themselves are designed and ready, the robot design ended up being very straightforward. 6 joints for 6 degrees of freedom, each joint being a belt-driven actuator. The second and the third joints have 2 actuators because these are the joints that do most of the heavy lifting and hence need more torque. I feel that this is where this approach of using an independent actuator made my life quite easy. It helped me keep the design modular. All I had to do was to create links between the joints. Then with the design complete, I could just duplicate the actuator assemblies and 3D print the connecting links. Post that, it was time to start building. The first joint, which is driven by a NEMA 23 motor, sits directly on the base of the robot. Joint 2 has 2 actuators driven by NEMA 23 motors. Each actuator is controlled by the same controller, but they have their own stepper driver and battery. The assembly and the logic is exactly the same for joint 3, but the only difference is that the actuators use NEMA 17 motors. Joints 4 and 5 use the single stage actuators. And finally, joint 6 is driven by this small NEMA 14 motor. This is what the robot looks like in all its glory. Let's test it. So now we know it works, but there is a lot more that needs to be done in terms of testing the performance and the capability of the robot. But right off the bat, here is what worked with this approach of using completely independent joints. The 2-stage belt-driven actuator itself is quite capable and works very reliably, especially after the latest improvements. As I mentioned before, it really makes the design modular. I could just duplicate the actuator assemblies and create links between them to complete the design. The control and the communication protocol is working really well. ESP now has a very quick turnaround time and the connectivity is reliable. The use of a separate microcontroller for each joint offloads a lot of the processing to the joint controllers, relieving the central controller of this load. All the central controller has to do is send joint position commands, and the individual joint controllers will take care of things like processing the feedback from the encoder and PID controller, creating a nice decentralized system. Wire management is way easier with this approach. You don't have to worry about wires getting tangled with each other when the joints rotate. The wires for each joints rotate with the joints. Now, what did not work with this approach? Just two things really, but these could really be deal breakers in using this approach in practical applications. First is that because each joint needs its own battery, that is additional weight the robot has to carry. And then because we want to minimize the weight of the batteries, our options are very limited in terms of which batteries we can use and how much current capacity they have. The second problem is somewhat related to the first one. The current limit of the batteries and the stepper drivers does not allow us to use the full torque capacity of the stepper motor, restricting the maximum load the robot can lift. A middle ground solution for these problems can be to run two wires up the robot to power it, and I'm seriously considering giving this a shot. Despite these drawbacks, the actuators and the robot's hardware and design still have a lot of potential that can be explored. I have grand plans for that. If you want to follow the progress, please subscribe to the channel. Was this project a smashing success? Not yet, to be honest, but it provided some excellent learnings. I would really like to know what you all thought about this approach and if there are any ways in which I can make it better. Please let me know in the comments below. If you liked the video, please hit the like button and subscribe for future updates regarding this project. See you all in the next one.